Hey guys, I'm sorry I haven't posted in a month. My mocks were going on and had absolutely no time to make any of these videos. So anyway, today we'll be going over the fundamental theorem of calculus. Um, and as you remember in my previous video, we learned that the average value of a function between a and b is the integral between a and b of that function, that be f of x, over the size of the interval, that is b minus a. So and this integral really represents the area underneath the graph, the area between the function and the xy axis. So let's say we have a function. So let's say we had the function that looks something like this. That's y is equal to fx, right? And let's say that we're looking at the value of the integral of the function at different values of x when it's integrated, and therefore let x be some point over here, right? And so since this will be the integral from 0 to x, this will be the area under the graph from 0 to some point x, and let's say that point is somewhere here, but this actually could just be anywhere on the graph. And so for now we will look at it to be this area. And since this is continuously changing, we can say that that would be another continuous function f of x. And this is an assumption that we're making, but since this would actually have a very long proof, we'll just assume that to be true. So let's say we want to find a small change in this value x. So let's say that that small change is this value dx, right? As we remember, that was another word for delta, another representation for delta, because it's an infinitesimally small change. And but just for now, we're gonna show it as a finitely large change. So looking at the area, the change in area, because that would give us the change in this function, we can assume that this is a rectangle because this dx is that small. And so this area, or this change in the value of f of x, which would be the change in the area, the change in this area, would be this dx times the value of the function at that point, right? Because this little rectangle would be the value of the function at that point multiplied by this dx, so f of x. And we are assuming that this rectangle is the value of the function at the point x, and then multiplied by that dx. And since when dx would become extremely small, that would be equal to the real change in the function. Although right now it would be an overestimate, or depending on which side of the function we are, it would be an estimate. But as that gets smaller, as that dx gets smaller and smaller, it becomes an accurate change for the change of the area, right? And since we know that the function of the area is f of x, we know that that would be df, since that is the change in the area. And therefore we can say that f of x is actually the derivative of that function f, right? And what we have shown is that the derivative of this function is actually equal to that function, which basically tells us that if we want to find the integral of any function f of x, we want to find the derivative of which function gives us f of x. And as an example, if we want to find the for example, if we want to find the integral of sine of x, we need dx. We need to think about the derivative of which function would give us sine of x. We know that the derivative of cos of x gives us negative sine of x, and therefore the derivative of negative cos of x would give us sine of x, right? So d of negative cos of x dx is equal to sine of x. And therefore the integral of sine of x, I'm going to write this here, the integral of sine of x dx is actually just negative cos of x. And we would have to put some limit from 0 to x, let's say, of sine of x dx would be negative cos of x. So now that we know that, now that we know that the that the function for the area under curve from 0 to x would just be the antiderivative or the opposite or the derivative of the function that we're taking the integral of, we can say that if we're taking the integral between 2 points, let's say b and a, of f of x dx, that would be equal to f of a minus f of b, where the derivative of f of x, that's f dash of x, is equal to f of x.